propuestas, podríamos hacer unos fondos como para un par de veces al año invitar a alguien de afuera también, dentro del país, dentro de lo posible. Y si no, si sabemos de gente que viene o gente que está cerca de Bariloche y es interesante con el coloquio, haga la propuesta y la comisión de coloquio la analizamos. Hoy tenemos un orador invitado, Canfield, que ha sido invitado por el programa Maldacena, pero lo voy a dejar a Néstor, que es quien lo invitó, para que lo presente. Así que Néstor, te dejo la palabra.
Bueno, buenas tardes a todos y todas. Nos tocó este día muy particular con el clima para este coloquio. Es realmente un placer para mí poder presentar al profesor Canfield, que viene invitado por el programa Maldacena. El profesor Canfield es Senior Researcher en Ames Lab en Estados Unidos y además es profesor distinguido de la Iowa State University. En particular, él es uno de los hacedores de muestras más famosos del mundo, en particular en muestras de alta calidad en forma de nanocristales. Tiene alrededor de 1.300 publicaciones, alrededor de 50.000 citas. De vuelta, es un referente, es una persona extremadamente motivada. Creo que para todos los estudiantes que están acá es muy importante poder contar con él aquí hoy, porque de vuelta es una fuente de inspiración para todos aquellos que elegimos hacer ciencia. Hacía mucho tiempo que yo esperaba que venga a visitarnos, se dan esta oportunidad y bueno, nada, de vuelta. Yo me siento profundamente feliz de contar con su presencia acá hoy, también con su esposa Canfield, con quien hemos tenido una relación durante los últimos tiempos a partir de una visita que yo hice al laboratorio de ellos y también una colaboración científica. Paul está acá, llegó el lunes pasado. Esta semana nos dio un seminario de materia condensada que se hace en la división de sólidos, dentro de sólidos de la división de bajas temperaturas. Va a estar acá en el laboratorio de bajas temperaturas hasta el miércoles que viene, se va el jueves porque el viernes que viene da el coloquio en la UBA, en el departamento de física. Cualquiera que quiera venir a visitarnos e interactuar con él puede hacerlo, puede sentirse libre de poder hacerlo. También está dando un curso de crecimiento de muestras que empezó durante esta semana, tuvo una clase el martes pasado y otra clase ayer, y tiene una última clase sobre caracterización de materiales que va a ser el próximo lunes. En particular, a lo largo de su trayectoria, Canfield ha trabajado en muchos materiales, se destacan los borocarbon, el magnesio boro 2, también muchos superconductores basados en hierro, y muchos materiales tanto también interesantes desde el punto de vista magnético y con aplicaciones en computación cuántica o propiedades topológicas. Nada. Thank you very much for visiting us and please take your time.
Absolutely. Thank you. That introduction is longer than my talk. So I apologize. I will do this presentation in English. My Spanish is limited. Estoy limitado porque no sé este lenguaje. So it's better if I do it in English. So whatever. That was not me. Maybe that was a response to my dad. Sure. All right, very good. Then, what I want to do is give a broad sense of how to make materials, a little bit about the mindset of finding materials, and then give an example of one class of materials that's sort of near and dear to my heart and near and dear to a lot of the researchers here, which is looking at superconductivity. So that's sort of the course agenda. This has been done in collaboration with my current group. Sergey Woodco is my longtime collaborator. We've been collaborating along with many marriages. Hakel Higuero is a recent addition to the group. This is our current collection of graduate students, undergraduates, postdocs. And this has been done with many postdocs, graduates, undergrads, visiting students, staff, researchers, etc. So,
wait a second, because it's very hard to stop.
is that like off? Is that like off?
Sí, está apagado.
I don't need it. Like, they want to leave it out of the record. Yes.
¿Se escucha bien atrás?
better if I'm up here away from the speakers? Yeah, I have to use both hands. No, that's asking too much coordination. I can walk and chew gums, that's about it. All right, good. So, done with lots of people having lots of fun. Good. Let's make sure we have this correct. Yes, there. Whoops. That's there. So, part of the visiting faculty that have come and kept us company. So, we live in a material world, okay? Madonna sings about it. This has been recognized by historians. We have epics named after the material du jour, or du century, Stone Age, Bronze Age, Iron Age. For the last 75 years, I would say in the Silicon Age, or more to my heart, in the age of novel materials. Virtually every device around us is the result of materials that have been optimized over the last 100, the last 50, the last 25, the last 10 years. This little miracle is a gift from solid-state physics, from electrical engineers, from material scientists. Some of the stuff in here was being researched as little as a decade ago. Okay? So, the question then is, for this talk, I want to give you an idea of where these materials come from. Whereas astronomers, NASA, high-energy physicists, etc., are fantastic at advertising their discoveries to humanity. Condensed matter physics is pretty damn poor, okay? Because most people don't realize that these materials haven't always existed. They're a result of us actually working and doing research. And if there's one thing as a community we can do better is communicate this to your aunt, your uncle, your abuela, and even if it's in the Pink Palace in Buenos Aires or in the White Palace in DC, because they just don't understand. And it's not good for us, it's not good for humanity. So, where do the materials come from? How are they developed? Well, basically, by searches through phase space, identifying regions of interesting physical or compositional effects. Now, phase space is a jargon term. This is supposed to be a general talk. So, phase space, it's an area you try to search, okay? This is a map of Ames, Iowa. If you've ever been to Iowa, it is a two-dimensional phase space. Okay? All right? And this is something that is yummy. This is called the morel mushroom. It is delicious. It pops up magically at certain times during the spring, and you just don't know where to look for it. I have been told you go under a pine tree, you do this. I have explored this phase space, and I have not mastered it. Man. Okay, so here's another example of a phase space. This is the open sea. It looks sort of big and inauspicious. On the other hand, for millennia, fishermen have known how to master this phase space. They are useful to their community, they are useful to their village, because they can find the samples they want in this phase space. What I want to do is give you an idea of how you can fish compositional or physical phase space for the materials or the effects that you're interested in. Okay? But what phase space am I talking about? So, in the interest of full disclosure, I need to, say, look, I'm a physicist. I use new materials design, discovery, characterization as a tool to do the physics I'm interested in, right? But what phase space then? Well, if we're going to talk about this, we're going to talk about a phase space that unfortunately many scientists, many physicists, many condensed matter physicists are less familiar with than they should be. And that's because they took the same damn quantum mechanics course. And that quantum mechanics course said, there's hydrogen. We know about hydrogen. There's stuff like hydrogen, there's stuff less like hydrogen. There are hard metals, there are semiconductors, I'd like to find that in my backyard. This might not be real. The students know this is not on the final exam, and that's bombs and nasty stuff. And that's hard. By the way, there's an advanced version of this. So, this hurts your fingers, that changes your voice. Okay. And look, I have a colleague. Yeah, I'll get to why I have a colleague story in a minute. Okay, so this is a travesty. The periodic table is the palette you paint with. It's the pantry you choose your ingredients from. It's the Lego set we build every known and unknown material. It's a joy. It's a fun toy box to play with. But to show the ignorance of my colleagues, I had a condensed air experimentalist. We were doing substitutions on iron-based materials. We'd substitute all these things. And he told me, Paul, why haven't you substituted the element above iron? And I was deeply confused. But, yeah, so this is what we work with, okay? And we need to be sort of familiar with. Great. If you know how to cook, you can make the meal you want. This is a small subset of the ingredient cuisine periodic table, sort of on the vegetarian end. But if you know how to cook, you can make lots of tasty treats and you'll keep yourself fed and enjoy yourself. Okay? If you know how to discover and design materials, here's what you can cook with. I can have a binary quasicrystal. I can have a quaternary superconductor. The periodic table has roughly 100 elements that you can create all the known, and I emphasize again, and unknown materials. And that's fun. It's a pleasure. It's a privilege. Okay? So, sticking with food, you know, depending on your ingredients, you do different things. You do something different if you have pork chops or ground pork. Ground pork's fine. But today I'm going to emphasize pork chops, at least at the beginning. So, for studying physical properties of materials, you can look at crystalline or polycrystalline materials. For this talk, I'll focus on single crystals, and that brings up the question, why do we want single crystals? And how do we grow single crystals? And off-screen, and what do we do with them when we find them? That's the agenda for the talk. It's not all that profound. Okay, so why single crystals, part one? Okay, I come from an agricultural state. At a certain point, the corn is as high as an elephant's eye. And when that's true, you can appreciate that a single crystalline cornfield, God, this is a horrible screen. These were supposed to be nice parallel lines. Okay? No, trust me, on the computer it is. So let's look here. When the farmer plows a single crystalline cornfield, at a certain angle you can see through it, and at other angles you can't. This is an anisotropic optical property. Okay? Now, if the farmer is perverse, drunk, or the land requires it, you can make a polycrystalline cornfield. But then, no matter how you look at this, you're not appreciating the fact that this has anisotropic optical properties. Okay? Now, I've got optical, but when you look at a crystal, you can have an anisotropic, magnetic, electronic, thermal, mechanical. Any of these can be anisotropic, and the anisotropies tend to be hidden if it's a polycrystalline material. So, one of the reasons is to appreciate anisotropies. Another is these things are called grain boundaries. Often you have strain, other problems, impurities at grain boundaries, and generally, not always, but generally a single crystal is a higher purity material. So, if you want to understand a new material, if you want to understand the intrinsic physical properties, a single crystal makes it easier. There's some measurements that can only be done on single crystals. Many measurements are easier on single crystals. Once we understand it, once we have mastered it, if we decide it's useful, that's a big if, then we can decide whether it's going to be used in single crystal or polycrystalline form. But to understand it, single crystals are nicer. That's part one. Part two, they're pretty. And we laugh, but it's true. You don't get into this field for the rock and roll lifestyle. You're not getting into this field to snort cocaine off of the backs of friends. Friends of negotiable affection. You're doing it because you want to have a proximity to nature. And when you open up a growth ampule and see for the first time in the history of this part of the universe, a new phase with shiny facets, it's a moment of zen. You can stop, you can appreciate it. And then you can figure out what measurements you're going to make. But it's just a moment of joy. And look, if you're going to go into research science, you need to find your moments of joy. And this is just, for me, one of them. So, lovely. Good. New materials development, single crystals growth is done with very modest equipment. These are high temperature pizza ovens. Okay? I have high-tech cutting devices that you can also liberate bicycles, sell them, and fund your research. I hear Nestor's been funding his research for years. If you're missing your bicycle, talk to Nestor. Okay? Right. You have a centrifuge. We'll get to the centrifuge in a minute. I'm very happy we use in my lab about 92% of the stable elements on the periodic table. Woohoo! You know, that's nice. You get to work with high purity elements. Good. The spaces are small. It's not a synchrotron. It's not a Arecibo. It's not a neutron reactor. Okay? Crystal growth like birth can be messy. But on the other hand, it's a fantastic, addictive experience. It's spontaneous symmetry breaking at its best. I was teaching a master's course in Madrid at UAM, Autonomo, and one of the master's students opened up a growth, saw a crystal. He had grown guapissimo. No, it is, because it is guapissimo. And it's addictive. You know, if you want, it's sort of like selling drugs. You give away food first. You know, let the student grow the crystals. It's like, I own this, I made this, I can measure this. That's awesome. You know, I like this field because I get to make it, I get to measure it, I get to analyze it, I get to write it. Look, high energy physics is lovely, but you're the 1 out of 500 wire chamber winders on the left in a collaboration of 10,000. Not for me. If you're interested in Byzantine politics, great. But this is lovely because you get to own it all. So, with apologies to my high energy colleagues ever. Great. So, let's see how this works. First, you need an idea. That's the hard part, okay? I gave a seminar yesterday, day before, about where do ideas come from. Right now, let's just assume you have an idea, but that's not the first step's a doozy. Okay? But if you have an idea, then you might as well check out what humanity has to say to advise you on this idea. In the same way that if I say, I'm going to drive to Bolivia. Well, I'm from the United States, which means my sense of geography sucks. So I better look at a map to figure out where Bolivia is. I think it's north. Okay? But in the same way, if you have an idea if you're going to grow something, okay, look at a map. And that's a phase diagram. Okay? Because look, here's a map, and here's a binary phase diagram. Pure silver, pure barium, temperature, mixtures of. Look, at the most fundamental level, liquid, liquid, solid, solid. I'm going to teach you briefly how to read this map. Okay? And then we're going to go on with how do you grow things and then other good stuff. Okay? Good. Lovely. So, again, pure silver, pure barium, temperature, and mixtures. Okay? So, at highest temperature, we have a uniform liquid. That's nice. It's a single phase solution. If we look, there are these minima in the solution. These are called eutectics. Often we like to grow crystals out of solution, so finding where you have nice puddles of solution is useful for the growth. If you're already saying, come on, this is beyond my experience, I would say, no, it's not, because it's snowing outside. And at least in the US, when it's snowing outside or it's icy, people who don't want to shovel throw salt. Okay? And what you're doing with the salt is you're lowering the melting point of water from 0 Celsius all the way down to as low as possibly minus 21. Now, you guys don't have really cold weather here. Where I come from, it can be minus 30. Okay? At minus 30, throwing salt on the ice doesn't do you any good. But as long as you're above minus 21, you can get a liquid because you can drop into this eutectic. Okay? So, many times in winter, you're taking advantage of eutectics. Lovely. Other point on the phase diagram. This is pure silver. This is pure barium. This is silver 2 barium, silver barium, silver 2 barium 3. These are unique, different crystal structures. Okay? If they're shown as a line, it's called a line compound, and it means they only form with this exact ratio. Some compounds can have widths of formation. Silver 5 barium, it can form with a little more, a little less silver, a little more, a little less barium. If you're an engineer, you go, fantastic, it's tunable. If you're a basic research scientist, you go, catastrophe, reproducibility is going to be a problem. So, the good Lord giveth, the good Lord taketh away. But these then are the compounds that you could possibly form here. Now, this is the interesting part. This is what we're going to focus on. And as in politics, as in nation states, the borders are often where the action is. Okay? So, this is called the liquidus line. This separates the uniform liquid from multi-phase regions. Okay? This is the liquidus line for silver. This is the liquidus line for silver barium. Okay? Why am I pointing this out? If we start with this composition at high temperatures, it's a liquid. It's still a liquid. It's still a liquid. But now, when we hit the liquidus line, we start growing crystals of silver barium, and the remaining liquid becomes more barium rich. If we want to grow crystals of silver barium out of the solution, we identify where is the liquidus line, and we hit it upon cooling, we can grow our crystals. That's the essence of how you try to grow a material. So, let's look at a real example. I can show you what's involved. Okay? Because the point of this is just to give you a sense of what is this experimental science that I'm utilizing. Okay? So, I have had an idea. Let's grow cerium antimony 2. It is a metallic, micaceous, magnetic, topological, fascinating material. Yay. Good. Let's make some. Here we have the liquidus line for silver antimony 2. I'm going to hit it here out of excess antimony so I can grow crystals. What's involved? Well, I need to hold this molten cerium antimony liquid in something. My hand doesn't work. Okay? So, I'm going to use an alumina crucible. This is polycrystalline sapphire, if you want to think of it that way. Okay? I have an alumina crucible, and I'm going to have to protect these from air, so I'm going to seal it into a silica, amorphous silica tube. I use a hydrogen-oxygen blowtorch. I get this somewhere around the order of 2,000 degrees Celsius. I melt it, I flatten it, yay. Good. Nice. Now, what do? Well, I fill the bottom crucible with a lot of antimony, a little cerium. I put this filter, a fritted disc in here. I seal these in, I put these into these tubes. And I put a bunch of quartz wool on top, because that's a cushion. I'll explain the cushion in a minute. I take the blowtorch, I make a nice hourglass-like thing. This is still connected, so I can pump. I hook it up to a pumping manifold. I do mechanical vacuum, backfill with argon, rinse it a few times, and then seal it off with the blowtorch. So, I now have each growth. The crucibles are down here. This is the silica wool cushion on top. There's the seal. I can put them into my furnace, and the furnace, for those of you caring, that's a thermocouple, a hearth plate. I have heating elements above and below, and I close the door, and I heat it up. I dwell, I slowly cool down, I hopefully have grown my crystals, and now I'm sort of left with a dilemma. Okay? If you grew salt or sugar crystals out of water, you can pull it out of the water. If you grow salt or sugar crystals out of water and cool the water down to minus 100 Celsius, then your sugar crystal's stuck in ice, and you would say that's sort of a stupid thing to do. Well, the problem here is I'm growing this out of antimony. Antimony solidifies at about 600. I can't pull it out, so I have to pour off the antimony. Now, if you step out of the shower and there's no towel, you can just go, am I dry yet? It takes a while. Or, even without towel, you can just do something like this, and you can get a lot of the water off. Water is not that viscous. Liquid antimony is rather viscous, so the way to really do this is to take your ampule, invert it into this, you got that little cushion, and use the centrifuge, and get somewhere between 10 and 1,000 G to just squirt all that antimony to the other side. Okay? So remember, we had this fritted crucible. So that means I'll have my crystals here and all the nice liquid there. And then it solidifies in. It's good. And as a result, you can end up with beautiful plate-like metallic micaceous cerium diantimonide. If I were to write this in my lab notebook, I would just say cerium diantimonide out of antimony, self-flux, 5% cerium, 95% antimony, 1190 to 700.
Oh, excuse me.
Yes, sir.
You're
There are no chocolates today. Oh, no, just as long as you're not expecting it. In the classes, we give people chocolates, and he asks lots of questions. Yes.
You put the arrow there in the liquidus at a rather low temperature. Wouldn't it be better to go to a higher temperature to get the faster dynamics?
This is 1,200. You're saying, why don't I move this up here? In many cases, I want a single crystal. If I push up here, I'll have crystals interpenetrating and twinning because I have more material to grow. So there's a delicate balance here of I'm greedy, I want a big crystal, but I'm not so greedy that I want lots of big crystals interpenetrating. So there's a delicate balance there. Often it's an interplay between how densely is it growing, how quickly is it nucleating, etc. No, it's a fair statement. My only limit is silica softens at 12, and I want a single-phase liquid below 12. Good. On with it. Good. Let me look at one other sample, and then we'll get to measurements in superconductivity. But I just want to give you an idea. What about cerium monoantimonide? And this is sort of going back to part of what you were saying. Look, this is a beautiful material. Oh my God, it's rock salt. It has more magnetic phase transitions that you can throw a rock on. I think it has 20 different magnetically ordered states. It's fascinating. But you would have to, if you wanted to grow it just by solidifying the melt, you'd have to be around 1,800. You'd have huge vapor pressures. Things would be attacked. It would be very entropic. So lots of entropic disorder. But this is the wrong way to go about growing this, because does anyone in the audience happen to know what temperature sodium chloride melts at? 801 degrees Celsius. Almost no one makes sodium chloride crystals by heating it to 801 or 802 degrees Celsius. You do it by dissolving it in water or something else. So this is rock salt structure also. Maybe I can dissolve it in something. It doesn't dissolve in water very well. But I can find something like water. So when I was faced with this problem 35 years ago, there are virtually no ternary phase diagrams, just due to the combinatorials. We have most binaries, but when you do, 99 times 98 times 97, it becomes just a big number. There aren't that many of these. But what you could do is you could do experiments. So I figured, let's look at the elements that are lowish melting, that can dissolve cerium and antimony, sort of the Casablanca approach of round up the usual suspects. And what I found is tin works. So let me explain what's going on here. We've been looking at binary phase diagrams. It's now a ternary. Cerium, antimony, tin. This is the compositional plane of a ternary phase diagram. Any point here is a unique combination of A, B, and C. Now, if you want to get temperature, you have to have an extra axis. So a ternary phase diagram becomes a topological map. If you're putting in a ternary melt and seeing, what will I grow? It's the moral equivalent of getting in a helicopter, putting on a snowboard, putting on a blindfold, putting on a parachute, jumping out, and waiting to hit the surface and then skiing down. Because what's happening is, I'm coming in from above, I'm hitting the liquidus, and then I'm going down it. And I'll see what I get. Okay? Experimental physics. So, if we want to put this into the language we've just been discussing, I want to grow cerium antimony. I'm starting with a composition that is super tin rich. I can take this cut, and this is called a pseudo-binary. I've got tin, I've got cerium antimony, and I'm hoping to hit the liquidus line for cerium antimony. And since I'm telling you the story, it obviously works. So if I put in 5% cerium antimony and a lot of tin, heat up to 11, cool to 800, I can get these beautiful crystals of rock salt cerium monoantimonide. They have super high purity. I get triple R's. I'm sorry, this is an expert jargon of 700. They are lovely. No tin contamination. You can do lots of good stuff. So, up until this point, I've been explaining how, as a fine gourmet chef, we can create amazing, delightful treats for research. But the fun is, as a research physicist, you get to be the gourmand as well. So I not only get to make it, I get to enjoy it, I get to eat it, I get to play with it. So, what do? Well, in my group, we try to study the basic properties. So these are quantities. Some of them you teach in your introductory physics, chemistry, thermodynamics course. We measure magnetization as a function of temperature, field, and it's a single crystal. Angle that we're applying the field along. Specific heat, resistivity, Hall effect, thermoelectric power, thermal expansion, magnetoresistance. We generally measure between 0.4 and 350, although we can go up to 1,000, we can go down below 0.4 if we have to. We have fields up to 14 Tesla. We also use pressure as a variable. We can go to 3 GPa, 6 GPa, 10 GPa, 80 GPa, 100 GPa, depending on the cell, and we can push things around. Okay? Crudely, the idea is think, make, measure, think. And damn it, the think part is hard. Okay? No, making and measuring is easy. Monkeys can do that. It's the thinking part that's hard. Okay? Look, poetically, when we make a sample, when we do a measurement, we interview Mother Nature. And the nice thing is, she always answers. Sometimes the answer is obvious. Are you a superconductor? Yes. Are you an insulator? No. Sometimes the answer is cryptic. Sometimes the answer is, that was a stupid question. And then you have to figure out what's a better question. But again, this is the nature of experimental science. So, what do we look at? Well, what's on the menu? My own group looks at almost anything that can happen in a metal, or we're looking at the interaction between conduction electrons, the crystal lattice, and magnetism. Superconductivity, with and without magnetism, metal to insulator, ferro, antiferro, spin glasses, quasicrystals, diamagnetism. The list does go on. Generally, we try to do this by designing or discovering systems that let us ask sharp questions, and we hopefully can get sharp answers. Although sometimes, we just jump into a Turner and ask nature, what do you got? And that's fun also. So, since time is limited, I will focus on superconductivity for the rest of this talk. Okay? So, superconductivity is a bit over 100. She doesn't look a year over 75, but it's been around for a while now. And since the very beginning, you've had two competing drives in superconductivity. From the basic science point of view, it's an example of a quantum coherent state. All of the electrons conspire to organize together and have no resistance. How in the dickens does that work? Okay? But even Kimberly noticed soon after the discovery, it's technical. Zero resistance. If you have anything that's limited by I²R heating or resistive or anything, this beats it. Onus was immediately thinking high field magnets. Okay? So you've got basic technology, basic patent, no, what? So, in addition, superconductors have perfect diamagnetism and interesting electronic properties. Okay? They are compelling ground. So, how do you identify a superconductor? Well, zero resistance is often the easiest. Here is a beautiful magnesium diboride wire segment. It's a nice metal. It has a good ratio of resistance from high temperature to just above superconductivity. But then, a little above 39 Kelvin, zero resistance. Okay? Zero resistance. And it really is a zero. There have been studies where you set up persistent currents and loops, and it has no decay over the lifetime of a student's thesis, which is one step away from infinity. So, really, real zero resistance. Now, in addition, you have this neat flux repulsion. So, if you have a superconductor above TC, magnetic field's just going everywhere. Below TC, it gets expelled out, and this gives rise to diamagnetic levitation and other neat and groovy things. Okay? Superconductors' most conspicuous uses are taking advantage of zero resistance, usually in magnets. Okay? These can be really high field magnets where the high field is in a volume the size of my thumb, or it can be significant field magnets where the significant field is big enough to stuff a not too large human into. Okay? So, this is MRI. So if anyone asks you, gee, what do you do? Do I have any experience? You can say, have you, your mother, your aunt had an MRI? You were proximal to a superconductor that I was working on a decade ago. Or something like that. So this is a conspicuous use. Now, another one is they can carry huge current densities. So I have been told that real estate above ground in New York is expensive. It turns out real estate underground in New York is expensive too. So if you want to have more power in New York, you either need to buy more real estate and drill more tunnels, or you can retrofit the existing wires with superconducting wires, and then have much higher current densities and not need to deal with the real estate. Okay? So you have prototypical pilot plants of high TC superconductors where they're trying to see if this is really viable. Now, this has been prototyped for the last 3 decades. The first decade was prototype, it's coming soon. The second decade is a prototype, we're almost there. The third decade, oh my God, it's just weeks away. And show up. We'll see. Okay? Good. On the other hand, superconducting technology is mature. This is a cross-section of a niobium-based low-TC superconductor, and it's just beautiful. This is multi-filamentary. This is what you use in a high-field magnet. This is not science fiction. This is reality. In addition, for the high TCs, you can make wires made of various superconducting ribbons, and these are actually carrying high current densities and working also. Okay? At the grossest level, we want to have higher TCs because the cooling power scales with temperature. The colder, you need more power. Doug Finnemore, my mentor in superconductivity when I first came to Ames, was quoted in the early days of high TC, okay, as saying, cooling with liquid helium is like pouring out 18-year-old scotch. Cooling with liquid nitrogen is like pouring out cheap beer. Okay? It gives you an idea of what Doug's interests outside of physics were. But okay, he's still doing fine. Okay? So, if we want to think of superconductivity, I've been talking about TC, but as in all good things, there's a trinity. Okay? You've got TC, you've got HC, and you've got JC. Okay? TC is the transition temperature below which it superconducts. So this is temperature and magnetic field. A material stops superconducting if it's in a large enough magnetic field. Okay? So it superconducts here, it's not superconducting here. There's another dimension. Here's TC. A material superconducts if the current density it's carrying is below a critical current density. So, if you want your MRI to function at 4.2, your field needs to be below this curve and below this curve. Okay? So, what do we want? We want to push both of these curves out. We want to push them out in a way that has cheap and safe materials. I don't want a new superconductor that's 90% platinum. I don't want a new superconductor that's even 10% plutonium. And trust me, both of them exist, but they're not going to be useful. Okay? And we want it to be easy to fabricate, because the high TCs are cheap, but they are a pain in various body parts to make, and they are expensive. Okay? So usually what we do is we discover TC, yay! And then we go, whoa, I can get a high TC, I can get a high HC too, and then we say, and maybe JC will be solved. And the reason we're doing this is we're physicists. JC is an engineering term. Okay? No, and I mean serious. And it's the death of superconductors. JC takes decades. The reason high temperature superconductors, which occurred before most of you were born, still aren't great, is JC has been a stone cold bitch. Okay? So, JC is difficult, and I will come back to that. So, if what we have is here, TC, H, and JC, humanity is greedy, we want that. Okay? So, let's see how we're doing. Good. A quick history of TC. Let's start with that, and then we'll go to other things. As I said, a little over 100 years, in the early 1910s, chemical minerals discovered elemental mercury, we got elemental lead, elemental niobium, and then it slowly marched up. Then we had the cuprates, and then all hell's broken loose. Okay? So there are basically two schools, the old school, the new school. I'll define these. There are bonus points and a complementary version of a fritted crucible set. To anyone who can identify both of these icons correctly, they will be shown again. You don't need to worry. All right. Old school superconductivity, originally found in high purity elements. This is the mercury, lead, niobium. Then it was found in binaries or other things, niobium nitride, triniobium tin, triniobium germanium. Basically, after World War II, there was a real push to go beyond elemental. Baird, Matthias, Ted Jabal, and others pushed it here, but then it was stuck at about 20 for decades. Superconductivity has been declared dead more often than zombies and vampires in horror movies. It rises from the dead and comes back again. And there have been some other resurrections that we'll talk about in a few minutes. Okay? Now, having said that, in about the 50s, you had the key idea. So this type of superconductivity is theoretically understood. The basic essence, and if you're a theorist, forgive me, I'm just going to give a schematic. But what happens is you have two electrons attracted to each other. How does that work? They're both negatively charged. Well, what happens is you have a lattice, the electrons going through it, it leads to a lattice distortion. This is called a phonon. Okay? Before this phonon can relax, it has a little net positive charge, it attracts in another electron. These two electrons form at a certain temperature something called a Cooper pair. Two electrons are talking, these have large coherence lengths, the Cooper pairs interact. This clearly depends on electrons, phonons, and their coupling. Okay? But then you can sort of understand what's going on, and here's an anthropomorphic analogy. Here's a mass of humanity. If someone over here goes, fire, it's going to be a very chaotic flow. Okay? On the other hand, if this mass of humanity is communicating, then it can organize itself into some coherent form and march around and not scatter and move more efficiently. Okay? So, this was our understanding of superconductivity, but it was sort of stuck at 20 Kelvin for decades. But then, in the 80s, came the copper oxides, and in less than a decade, TC rose from 20 to 130. It was a time of pleasure, euphoria. It was a time of pain, because physicists realized that quaternary oxides are not simple. It was complex materials problems. We still don't know the mechanism. These puppies are hard to work with. Until recently, this was the 800-pound gorilla of superconductivity. Impossible to ignore, hard to understand, divisive. But man, it's interesting. In the old days, I'm just looking at the old people here, okay? Sorry guys, you're old. Yeah, no, not I remember march meetings where you had 3 Nobel Prize laureates pissing and yelling and saying bad things to each other like horny cats. No, it was bad. And they were theorists, and it's because there's another prize in this. No, so it was a particular example of bad behavior in the field. Things settled down. People died. That's the nature of science. All right, so broadly speaking, there was a sense that TC is tapped by the excitation, giving rise to the coupling between these electrons. Okay, for phonons, it was thought for a long time that 20, then 30, then 40. Theorists are flexible, okay? You know, that's sort of it. Now, that's probably more or less the case at ambient pressure. We're turning to high pressure soon, okay? But when you go to 130, you immediately start thinking, well, maybe it's some other mechanism. And in the same way, here's a mass of humanity. They're not marching through Red Square. It would be a little cold. I think this is more on a beach in Florida. But we can organize this. You have things called contra dancing or square dancing. This is a great way of very quickly moving human mass across the room without scattering. And again, coherent cooperation. So maybe there's another mechanism in these cuprates, probably antiferromagnetic excitations. Now, having said that, we still don't know the mechanism for the cuprates, but you know what? It doesn't stop us from using them. Humanity used steel and iron long before we understood the metallurgy. We made arrowheads, swords, plows out of them. We're making wires out of these materials. We don't know the mechanism, but we know the empirical rules, and that's good enough. Okay, so the last 30 years have been a neat time for superconductivity. My research lifetime has been sort of blessed in superconductivity because we've had a whole bunch of interesting discoveries. So let me try to give you, in the small amount of remaining time, an overview of these. And I'm going to look at it through the lens, uncharacteristic for me, of applied physics. Okay? What I want to do is compare these materials to triniobium tin, niobium tin 3. This is a material that David Lavoisier and people worked decades to get the upper critical field to essentially 30. This is a highly optimized material. It's in most of the magnets in labs and even in MRIs. Okay? So I'm going to compare to this. First, I'm going to look at some examples of old school discoveries, orocarbides and MgD2, and then I'll talk about new school discoveries, the cuprates and the iron arsenides, and then I'll wrap up. Okay? So let's start in 1994, a little bit after the discovery of the cuprates. There was the discovery of two intermetallic-like materials, yttrium, palladium, 2 boron, 2 carbon, yttrium, nickel, 2 boron, 2 carbon. These had TCs that rivaled or even exceeded the niobium 3-tin niobium nitride. Okay? So it was like, oh, maybe this is exciting and interesting, and thank God they're not cuprates. Okay? So one of the bonuses was my group was able to figure out how to grow single crystals within a month or so after the discovery, so we can avoid dealing with polycrystalline results and confusion from almost the start. Now, in terms of applied physics, they're very disappointing. It has a TC almost identical to niobium 3-tin, but no matter what you do with it, you can't get HC2 much higher than 7 as opposed to 30. So these will never be a practical superconductor. In addition, lutetium is expensive, they're brittle, blah, blah, blah. Okay. Now, for basic physics, they were fascinating, because if you can grow something with lutetium, which is a rare earth, you can go into lighter rare earths all the way to gadolinium, and you can see that you have superconductivity and magnetism coexisting. It was a playground for understanding how they interact, but that's not today's talk. Now, on the other hand, in 2001, MgD2 was discovered. And this was the breakthrough that physicists like Doug Fenimore and others had waited their whole lives for. This was going from 20 Kelvin to 40 Kelvin. That's a doubling, and that's a significant doubling, okay? So that was really exciting. Okay, now, having taught you how you grow things out of binaries, here's magnesium, here's boron, here's temperature. The problem is there is no liquidus line. The liquidus line is asymptotically plugged here, which means as soon as you get a little boron and magnesium, you immediately precipitate out MgD2. You can't grow nice large single crystals this way. And boy, we tried a lot. We tried turners. But it doesn't matter. We figured out that you can get high purity MgD2 by reacting high purity boron with magnesium vapor. Okay? And we could confirm TC. We could establish HC2. We even came up with a clever way for polycrystalline materials how to infer the anisotropic HC2. Okay? But more importantly, if you look at the niobium 3-tin, pure MgD2 looks like it's disappointing. It's only going to 15 rather than 30. But this is very pure MgD2, and we figured out if we doped in a small amount of carbon, we could add 1, 2, 3, 4, 5%. We could get above 35 Tesla. So bulk carbon-doped MgD2 has an HC2 curve that supersedes niobium 3-tin. And in the past 25 years, this 20 Kelvin here has become known as the MgD2 zone of use. 20 Kelvin, niobium 3-tin doesn't superconduct. At 20 Kelvin, we can have HC2s 15 Tesla. Not bad. And 20 Kelvin means you don't need to use liquid helium. You can use cold helium gas cooled by a closed-cycle refrigerator. So this is a multifilamentary wire of MgD2. It can be wound into large Helmholtz configurations, and instead of having an MRI that's a little tube that you have to grease someone up to fit in, you can have these open access Helmholtz geometry, plug and play, you don't need liquid helium. This happened in my research lifetime. We went from, whoa, what the hell is that, to, hey, here's a product. No, that's amazing. You know, this is the nice thing about condensed matter physics, because it is absolute, basic, fundamental physics, but it actually can be applied ultimately in some cases too. That's not my gig, but it's nice. Okay? Now, what about the high TC compounds? So we can start with the goop rates. Copper oxide-based materials have a phenomenal increase in TC, but to paraphrase the late Alan Greenspan, despite the initial flush of irrational exuberance, it has been a long hike to make these into wires that work. Okay? And one of the reasons is they're highly anisotropic for their HC2, but the more profound reason is, given that this is a special type of superconductivity, if you have a kilometer-long wire, which you need if you wind coils or have power, every polycrystalline grain of the superconductor has to be oriented within a few degrees of each other, over the whole kilometer. That's not easy. And it's taken decades to figure out ways of making this so it works. And engineers and material scientists are phenomenal. They figured it out, but it's been a long haul. After more than 30 years of effort, we're almost there. And I update this. Maybe I'll say after 40 years the next time I do this. Who knows? But the new school has been a tough school. Now, in 2008, iron arsenide-based superconductors were found. And this was incredible. The TCs are not quite as high as the goop rates, but they are very promising in other manners, and they're much easier to work with. So the first two families were lanthanum iron arsenic oxygen, which was interesting, but this is a bit of a pain in the backside to make, and barium iron 2 arsenic 2, okay? And the neat thing is, barium iron 2 arsenic 2 falls exactly into how we grew cerium and timonite. Remember, we grew cerium and timonite out of tin? We could grow barium iron 2 arsenic 2, doped with some potassium, out of tin. As soon as I heard about this, I told my student, Nini, I know that we can have this within 2 days. Now, I say that about everything. I'm right about 20% of the time, maybe only 10, but this is one of the times I was right. This is the first single crystal of this material in the world. Lovely. What do? We have a single crystal, we can measure anisotropic properties. This is field, this is temperature, this is HC2, and this is 14 Tesla. That's not a small field. By 14 Tesla, we've suppressed this by only about 4 degrees. That means we're going to have a big HC2. We went to the National High Magnetic Field Lab. We took it up to 60 Tesla. The anisotropy is clear, but it's relatively small, okay? And remember, MgE2 zone fused 20 Kelvin, this is about 15 Tesla. 20 Kelvin, the lower HC2 is above 40 Tesla. Holy Moses! If JC can be made large enough, these will become practical superconductors. But remember what I said about JC. So if JC can be made large enough, these will become practical superconductors. If we have a 6-legged chicken, then there will be more drumsticks. This is how I use AI. How do I use AI in my research? Draw me a 6-legged chicken. All right, but I mean, hopefully we can do it, but this is the sin of the basic physicists. Okay? Yeah, there are 6 legs.
Yes, 7.
Oh shit, really? Oh, AI screwed with me. 1, 2, 3, 4. Points for you.
Chocolate.
She didn't bring it. You want a crucible? Oh yeah, I made a crucible. Look, I'm good to go. These are Canfield crucible sets. Don't laugh. Oh no, this is the innovation, the fritted disc. Over 1 million have been sold, and I get 0 pennies on the dollar. I just get the name. Erlenmeyer got his flask, I get my crucible. Okay, good. So, on with the show. So, with these iron arsenides, we did lots of different doping series to understand the rules. Pure barium iron 2 arsenic 2 is not a superconductor. It's just a crappy metal that has an antiferromagnetic transition. If you add a little cobalt and a little potassium, you lower the magnetic transition, you get a dome of superconductivity. Superconductivity is highest right where this goes to 0 at something that's called a quantum critical point. I point this out because this is darn similar to the cuprates. The cuprates have antiferromagnetism. As you suppress the antiferromagnetism, you get a dome of superconductivity near where the superconductivity goes away. Okay? Now, what's important to note is this is not even a metal. This is a crappy metal. Neither of them are superconductors to start with. Okay? So, this provides some insight to why are we finding so few high DC families. You have to find the right material and dope it the right way. That's the product of two small numbers, which my mathematician colleagues tells me is a very small number. Okay? So, this is one of the reasons it's a tough school. So, where are we? Old school, new school, old school, new school. The pendulum is still in motion. Okay? Let's get to current days. There has been a phenomenal discovery in the last decade by Mikhail Ames and colleagues. They found that if you can create under high pressures materials with lots of light elements, lots of stiff bonding, you can get TCs up to 200, up to 250. Okay? Now, 250 is hotter than an unheated barn in Iowa. It's almost hotter than the guest house room that I've been sleeping in because the heating broke. Okay? It's getting fixed. So, we don't have room temperature superconductivity, but we at least have barn temperature superconductivity. Now, these are obscenely high pressures. This is, a gigapascal is 10,000 atmospheres. So we're over 1 million atmospheres pressure. This is not practical, but it's proof of principle. These are thought to be old school BCS phonon-mediated superconductors. This is motivational because it means that maybe we can find other old school phonon-mediated that get us above 77, and then we hopefully won't have the problems we had with the cuprates. But this is one of the areas in superconductivity. It's exciting, but the pendulum is still swinging. So, what's the future? Okay? Well, we can sort of go back to where we started, searches through phase space. How can we find better superconductors? And I think we have two types of searches. Iconically, chemically based or physically based. Okay? Let's start with chemically based. Let's look and go through think, make, measure, think it's time to think again. Okay, we have high TCs, borochlorides, MgB2, iron arsenide. These are all materials that live between traditional oxide insulators and broadband metals. So, if we want to think about where to look, well, we can think about light elements, or we can think about tuning the band filling by substituting alkali earth for transition metals, and we can play with bandwidth. These are all terms we can map onto a Hamiltonian, and there are lots of interesting searches going on. Okay? Now, on the other hand, we can get a physically motivated search. We can say, look, the iron arsenide, the cuprates, these were all these fragile magnets that the magnetism got tuned to 0. If you want to find a new superconductor, that's not necessarily actionable, but if you say, let me look at other systems that might have fragile moments I can suppress, that becomes actionable, and people are looking for that as well. So, both of these types of searches are going on worldwide. This is a golden age for new superconductivity, and hopefully we're going to continue finding it. By the way, if you start hearing about emphasis on really wanting to finally get fusion to work, another thing that we've been hearing about is almost there for the last decade, for many decades, you need high fields. High fields are generated by superconductors, so we're, again, looking for good superconductors to generate these high fields. So, it is a promising time. So, more broadly, let me circle out. And for those of you who are semi-fluent in English, I apologize. For those of you who don't understand, you've been spared a horrible pun that has been 55 minutes in building. Okay? The morale of the story is Seeking ye shall find, what's unsought goes undetected. Okay? And the reason I say that is, remember this phase space that I said I failed to master? Well, I had failed to master it for many years, okay? But when I paid closer attention to home, literally in my own backyard, a couple springs ago, these puppies grew in my backyard. So you just never know what you're going to find. You just need to keep looking. So, there we are. There are fantastic surprises out there. We have the privilege and fun of looking for them, and every now and then we find them. And we get to interact with nature. We interact with the highest of temperatures, the lowest of temperatures, the highest of purity, beautiful crystals. It's a blessed life. So, thank you. That's all. DOE funds my work, and I happily take any questions you might have. Astronomer in back. Was that good for you?
Great.
Awesome. Good. No, I always have the astronomer as my caliper. All right.
Okay, thank you, Paul.
Oh, yeah.
Please go to talk.
Super.
Bruno, you have a question?
Yes. Oh, just yell.
Just speak up.
I have to see. In regard to the high fields that we need for fusion,
Yes.
what do you think the right superconductors choose would be for generating the field?
Let me start by the opposite question. The wrong superconductor would be MgE2. Because boron absorbs neutrons. And you would be quickly transmuting it. So you need to have superconductors that are relatively rad hard. Okay? So at this point, they're looking at high TC tapes and hoping they can get them. So this has been a renaissance. High TC tapes sort of died down for a decade or so. But with the fusion, they're coming back up. So you have both German and US firms really trying to see if that might work. Those are the ones they're looking at right now.
Tapes without gadolinium, I believe.
Yeah, gadolinium would be a bad choice as well. Yes, ma'am. Let's go id-coding.
Any more questions?
Back there.
I can just shout.
I think they're recording, so they want to capture it.
So did I understand correctly the theoretical understanding of high TC superconductors? Nobody has a clue.
Well, nobody has a clue. I think you've offended 3 generations of theorists. I think there are lots of clues, but there is no consensus and there is no falsifiable theory yet. Unlike a BCS electron photon mediated, where there is. So yes.
Thank you.
Sure. There's still opportunities. Quick, submit your paper today.
Okay, any more questions, please?
This is more out of curiosity.
Yes.
A couple years ago, there were some Koreans that claimed to have.
Yeah, that was what's known as a USO.
Yeah, it was just.
For the rest, unidentified superconducting object. No. and look, I'll take credit for my own jokes, but that is terminology in the field. Okay. And what was fun, I'll get back to your question in a minute, but I have to tell a story. During the Woodstock of Physics, which, I don't know, were you guys there? Okay, I was. So this was discovered, the press was there, and the press was going batshit crazy. So my bad behaved graduate students like myself, when you saw a press go in the elevator, I'd go to my colleague and, hey, did you hear about Milwaukee? Milwaukee University has a TC of 200. Isn't that amazing? Oh yeah, Milwaukee's great. And the press would, they go off. Whatever. Right? That was a USO. It was basically, I don't think it was fraudulent. Okay, I think they were just not experienced. This was a group that had very little experience in new materials. They had a ferromagnet. And if you have a partial ferromagnet, you can lift one side and not the other off of this. So you never had pure levitation. In addition, you never had any feature in resistance, blah, blah, blah. Yeah.
okay, that was one of my two questions.
Sure.
The other one was if you, during that week, that everyone was like, wanting to replicate the results, if you try to synthesize the...
No, because it was so clearly horseshit that I wasn't going to waste my time.
Oh, you knew from the start
I'm sorry, I've been doing this a long time. So no, some things you go, I think that's highly unlikely. If by some chance I'm wrong, after someone I believe has done something, I'll look at it, but no, that one made no sense. So, there we go. Say let me. It would have been interesting. Now, it was called LK, not, what? And it was out of Korea. And now, I know it isn't the case, but given everything, I say LK is for lucky Koreans. So lucky Koreans 99. Nestor will have to defend them, but yeah, no, it was just baloney. And you know, the field is proven. Look, this was an example of science working. Okay? There's a claim, people disproved it. Okay? Other questions?
Okay. Any more questions?
Yes, there, Nestor in front. Here, Nestor.
Oh, okay. I mean,
Hi Paul,
Hey.
so thank you for your presentation, it was great. Just to do some futurology, how positive are you on science finding this holy trinity of superconductors in which you have like all these flavors in specific way, like high TC, high critical current, high HCQ, and all of that?
Well, it depends what you mean by high. So, I think the concept of room temperature superconductivity is a stupid goal. Because there's nothing special about room temperature. Okay? We already have room temperature. Okay? But even if a material superconducted at room temperature, you would have to go well below room temperature for the gap to have developed, for it to have good properties, etc. What I would want, so I'm sort of answering your question backwards, like any good politician. What you want is a superconductor that has a TC 100K or more, because nitrogen is cheap, nitrogen is 77, pump nitrogen is 70. Okay? No problem. You want to have 100K or more. You prefer it probably to be electron-photon mediated, or maybe the iron arsenide, something that doesn't have this horrible, you have to granulate. Okay? The iron arsenides already have beautiful TC and HC2. One I didn't talk about that doesn't need to be doped is calcium, potassium, iron for arsenic fluoride. It's a well-ordered line compound, TC of 35, huge HC2s. Those are good even because 20 Kelvin is good. But if you want it just to be simple and not difficult, you want to get my goal, my desire, my fantasy is, 100 Kelvin, hopefully electron-photon mediated. It will probably have a good HC2, and 100 Kelvin in the clean limit. So then I can dope it, I can deal with it and try to get HC2 high. That would be wonderful. So you don't wait. The reason I went this way is so that high TC, high this, we need to define what we mean by high. 100 Kelvin would be fantastic if you didn't have problems with anisotropies of HC and JC, and electron-photon mediated generally avoid those problems. If I didn't answer your question, come back and force me to answer it. Good enough?
Yeah.
Okay, good
Good
enough.
enough.
I'm happy to have a
Do you
discussion.
believe your dream is achievable? Like
I
science?
think, yes, I do think it is. When? I will not make predictions about when.
Okay,
Okay.
thank you.
any more questions?
Way back. They're making, and the next question has to be in front. Come on, we need to make Nestor walk.
This is also a curiosity. Out of the samples you made, how many of the things you work on started as basic science and then ended up like applications?
I think I have 4 patents. I mean, and again, that's not a question, but it sort of is. So if you have a patent, it's allegedly applied. So patents for synthetic techniques of MgB2, patent for how to contact iron arsenide. I also work, and I haven't talked about this at all, we were looking for practical ferromagnets that are rare earth or use cheap rare earths. Okay? Cerium is a throwaway rare earth at this point. There's lots of cerium. If you can find a high Curie temperature TC ferromagnet with good anisotropy, and it's amazing, when you're looking for a ferromagnet and a superconductor, it's the same. You want a high TC, different Cs. You want, anisotropy in pinning. You want pinning of vortices, you want pinning of magnetic domains. So we worked on that. We found a very interesting cerium cobalt with a little bit of magnesium and other stuff. That turned out to be applied. Okay, so by the way, I just published a paper with Juan Schmidt, my Argentinian graduate student who's now at the University of Buenos Aires. Briefly, I think he's going to Madrid for a while. We found shape memory at room temperature. So we tuned a system that has this beautiful collapse and made it so that we could squeeze on it at room temperature. It stays squeezed, you can warm it, and then you could squeeze it again. So it really is a shape memory compound. So, and look, I had a lab partner as an undergraduate. His statement was, his ambition was to be an absent-minded scientist with a cheese sandwich in his pocket. And I love the concept of a cheese sandwich in your pocket because it's unnecessarily explicit. But that was my goal too. I'm just an absent-minded basic research scientist, but in condensed matter physics, you're so proximal to apply, you'll have to almost work hard not to be doing something that could be applied. Now, I'm looking at the most basic questions. How does magnetism exist? I'm like a voyeur peeking in the bedroom of the birth of magnetism. I can watch electrons being non-magnetic. Oh my God, they're magnetic now. So that's basic physics. Okay? But you can also have applied. Long answer to a short question. Did I answer it? Or do you want to come back?
No,
Okay, bueno. Someone up front. Here, she has a question. Nestor, quick. Rápido, muchacho.
Una actriz.
I had to think of a
Okay,
question.
one of the guys attacking. I was stronger, you're next.
I want to come back to the 7 or 6-leg chicken.
7 like I'm told.
Yeah, how deceiving AI can be. Just a few words.
I have a whole talk on that.
Just a few words on how AI, machine learning,
I know.
can help. You know what my question is.
I know what your question is. The
Okay,
answer
so
is
please
yes.
answer.
I have a whole talk on that. And I stole the 6-leg chicken from that, okay? Because some of my best friends are computational physicists. God bless them. Some of them are useful. I got her. No, some of them are useful, and we're trying. But for the last 30 years, every 5 years I'm told, oh, computational physics, materials by design, AI and ML is going to make you obsolete. And the problem is, so you might have heard of these challenges of protein folding. Okay? Those are fantastic. Protein is a one-dimensional object. And you've defined it, you ask how it folds. That's a limited phase space. I have worked with computational physicists, and originally, for the first decades, you'd have a ternary phase diagram, okay? And I would say, hey guys, is there anything interesting there? And they would go, blah, and they would sort of puke up 6, 12, 20 compounds that were at or below the convex hull, and oh, we're sure these will all form, and I spent 6 months trying to do, I do everything, I'm diligent, I try 10 different ways of making them, and none of them form. And then my dear colleagues say, experimentalists have failed to find them. And that's why I have my 6-leg chicken. Now, recently, I have inverted this process. Okay? And it's good because then we have arguments, well, do your compounds even exist? Well, my computer says yes, my experiments say no. And it's like arguing how many angels can dance on the tip of a pin. And it's a lovely argument, but it's useless. So, I've recently inverted this. Okay? This is what I call challenge. Okay? My talk is anchoring, benchmarking, challenging. Challenging is good. I periodically discover a new material with a new crystal structure. So traditional ML is going to have a little trouble with that. Okay. So I then tell my colleagues, hey guys, yttrium, cobalt, silver. There's no known compound. And I have an answer. I know what forms. I've solved the crystal structure. And they try. And the first time I tried this with lanthanum, cobalt, lead, we had 2 new structures. They couldn't find anything. And then we said, come on, guys. You need to try harder. They improved their codes. It got a little bit, they still couldn't find the structures. And pushing them further, there's a recent posting on Archive. They're using multi-minima iterative genetic algorithm. So genetic algorithm, if you're not familiar with it, is just like most mammals. You have 2 split DNA, they come together, you get a new object. Okay? So you take 2 unit cells, cut them in half, glue them together, relax it, and see what you get. That's genetic algorithm for discovering new materials. Okay? Now, multi-minima, as you can imagine, the energy landscape has lots of minima. Some are broad and shallow, some are deep. What they found they had to do is they can't live with the first answer, which is what they've been doing for dogs' years. What they do now is the first answer, they then fill this minima with concrete, or they put an energetic penalty for being there, and they search again, they find another minima, they find another minima, and some of these minima are deeper, and they keep doing this till they find the deepest minima. My rule is, if you find a new deepest, you need to go to twice as many iterations as you've done so far. When they did this for lanthanum, for cobalt, for lead, after 12 iterations, they found the right structure. So we are getting better, but they needed as input the stoichiometry, which is an experimental parameter, and they needed the number of formula units per unit cell. Okay, so right now, we're almost at the point of, if I tell you the stoichiometry, they might get the structure right. But telling the stoichiometry is hard. So if you say it's a ternary, so I've got AX, BY, CZ, I've got XYZ as subscripts. If I just say subscripts less than 5, think of how many different compounds. 111, 121, blah, 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 lots. And I said 5. Were you in class yet? Were you at the seminar yesterday? Yeah. Oh, okay, so you know what the answer is. So, do you remember the industrial ferromagnet of choice?
Yeah.
The subscripts? Oh, short-term memory problems. Okay, go on, Gladys, it wasn't that brutal. Okay, fine. Gladys, fine. She's saying, you remember the subscripts?
14, 5, 1.
No. 2, 14, 1. 14 was the important one. Neodymium 2. Iron 14, 1. 14! Imagine looking at ABC with any subscript up to the number 14. So, it's going to be hard. This was a super long answer, but it's close to my heart. So, is AIML getting there? It might be, but it's still far away from it because you've got this damn combinatorial problem of subscripts and complex energy phase spaces. We may get there, but I'm anticipating superconducting cables under New York before that. Yeah, but we may get there, but it's hard. Right now, AIML is like a 1.5-year-old that's still falling on the floor and pooping itself. Maybe it'll grow up.
Thank you.
You bet. Come on, someone back. Make Nestor move. It's been a long time. Thank you. You've been a great audience. I'm here all week.